before entering to Pyseg, we have to carry one more step, which is to make the masks be again of the size it has before the normalization. So for this is the step, resize tomo masks. So for this, we are going to look for a protocol called, let's go for tomo segment TV, a protocol called Resize segmented or annotated vesicles. This is very easy to fill. We only have to set the pointer of the input to the annotated and segmented membranes, where the output of the previous annotation protocol, and the tomograms whose size will be read, and this is the size which will the masks, the segmentations, will be resized to. So we have our tomograms, and it is very important, the original ones, these are the ones which were directly imported. And we execute, and with this operation, the masks will be resized and referred to the original tomograms instead of the denoised normalized tomograms. So all the picking will be carried out on the original tomogram and using the segmentations at that size. So you can see the output is a set of tomo masks. Now they are referred to this tomogram, and they share the same size and also the pixel size. So now let's go to Pyseg. In Pyseg, there are 4 steps that are the ones that has Antonio explained before, which are the pre-segmentation, the graphs calculation, the filament calculation, and finally the picking. And these are the 4 we are going to go through. So here in the documentation, you have a small introduction to.
Sorry,
Yep.
sorry, Jorge. Plus classification, unsupervised classification.
Well, I don't know what did I say. I was. I
Plus,
maybe the graphs. Yeah,
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 yeah.
yeah. After, I think I haven't. Maybe I used a very bad pronunciation. I didn't mention anything related to the classification. I was letting it to the final step, but for sure to the classification by Pyseg. Yeah, thanks, Antonio. Here you have a small introduction, which is just a small definition of conceptual definition of what this step carries consists of, or what operations are carried out on it. So let's go for the Pyseg. The Pyseg, as Antonio explained before, will provide us each member annotated in a more complex way, which means we have an index for the membrane, another index for the inner surroundings, and another index for the outer surroundings. So let's open the corresponding protocol. Let's look for it. Again, Control F for Pyseg. And these are the protocols that have been implemented. Hope that the last part of the Antonio's presentation is integrated soon, because it seems to be quite good. Let's start with the Pyseg membranes. And let me go back here and, oh yeah, I'm not the same as him. Okay. So You can here it's this protocol provides a double option to go into the Pyseg workflow. As you memory annotation tool exists, and like the rest of the plugins that are integrated in Scipion, they exist as a standalone applications or software packages which are executable. So, for example, if you have been working outside Scipion for any reason, and you have a star file that you have built for the standalone version of the memory annotator tool, you can directly import the star files. In our case, we are covering all the workflow inside Scipion, and so we are coming from a Scipion protocol. The first input must be the segmented and annotated tomograms. In our case, this is I think this should be this should be a mistake, because I think they have to be the tomo masks. Maybe it's a typo. So let's use the output of the Resize, which are the tomo masks. This panel can be used to split, in case it's necessary, to split the vesicles if they are too large into different sizes by cutting each vesicle volume, its subtomogram volume, into as many parts as specified using this X, Y, and Z number of cuts. Okay, offset voxels. In this case, we are going to use 44. This is the value we're going to use. Why is that? The 44 value is expressed in voxels and represents the width of a margin considered when cropping the vesicle. This means that if you determine an area which is very thick around the membrane, like in this case, because we're trying to pick ribosomes, so they're big particles, maybe you cut this area when you crop that vesicle in the new segmentation, more complex segmentation, the 3-area segmentation. So you can ask this to you can use this parameter to tell the algorithm, hey, leave a thicker margin when you are cropping to ensure that everything is contained in the cropped area. In this case, the one for example, one good practice is more or less to make some calculations. So, for example, in this case, I prefer to, for example, determine this parameter the last, because before you have more direct parameters, which are the segmented membrane thickness, which is, as said before, considered to be 60, considering the heads of the phospholipids. And in angstroms, we have the biggest ribosome size. It's about 300 angstroms, and we're going to let some error margin value at 10%, just to ensure that we are covering all the possible roundings in the calculations and so on. So if you calculate this, for example, you can say, I'm going to have this quantity of angstroms from the membrane to the outside. How many pixels are these? So you can calculate it. I don't have this, but you directly can calculate it by dividing by the pixel size or voxel size in this case. And this quantity should be zoomed to the 60. Armstrong of the membrane. So you have to more or less quantify 400 divided by 30.68. This could cover all of this. And you can also keep a couple of more pixels for margin to ensure that everything is inside. And this is how this value is more or less determined. Once again, if after the execution of the protocol, you see that your outer surroundings have been cropped, you can go back, do this, increase this value, and then re-execute. So with these parameters, we're going to execute this. And it was a small spoiler. It should be quite fast. I think in my machine it was about
I failed probably because I loaded the wrong file, because I'm one of those who had to copy.
Yeah, okay, it's okay. In your pointer, you have to copy. Let me check the project membrane. This one. If you are copying this, it should be pointing. You shouldn't need to do anything but executing.
No, I didn't. So I just copied the annotate segment membrane, blah, 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 and tried to go on from that point.
Okay. Okay. Or even there's a problem here.
Yeah, it looks exactly like it looks on your screen.
Maybe it was, I don't know, maybe it was missed during the migration. Let me point to the one I've copied before.
The output set of tomo masks?
Yeah, it's working fine. Yeah, maybe there was something which is generated meanwhile here that was not migrated. Okay, so for the ones who have been to copy from here, copy the resize segmentation, execute it, and refer and continue from there, copying the membrane and referring to it. And if anything goes wrong, just oh yeah, thanks to you, Tamara. Let me go back to the other project. I'll have both open, so two part 2. Yeah, okay, it has finished. So what we have here is more or less we can observe the results by as you can see, we have both here. You can click there, analyze results, and it will open two main screens. The first one corresponds to the crop subvolume. As you can see, these are our vesicles. The first one, the second one, and the third one. And this is the represented segmentation. I don't know why it's a little bit deformed, but it may be due to that other view. As you can see, it's here. The margin was enough because we are not cropping here or here. We are covering all the membrane, the inner, the outer surroundings, and a little bit of the background. So the cropping was correctly determined. And this is the point at we are ready to go into the graphs. So this figure was made just to keep all the time in mind which vesicles from the original data are our targets. So I think I've changed the order between this one and this one while I was doing, but this is just an illustrative to have all the idea all the time in mind. So sometimes, for example, as you can observe, this membrane is changing because it has not a regular shape. Oh, sorry, let me do it better here. We have the segmentation is not complete, but it covers as much as possible. So all these areas will be, in all these areas, that graphs will be traced. And this is what we are looking for. Not always in the real case, you are able to have this perfectly rounded segmented vesicle, and sometimes you have something like this. But playing as before with the parameters, we can have as much as possible of those membrane. So at this moment, we are going. Let just a small remarkable point, which is this one. We can do how to do this profile is very easy, and it's out of this scope, but I can show you just very quick because we are a little bit late, and I don't want to have you here more than necessary. But for example, if you double click on one of the results, for example, this one seems to be good. From this XMIP viewer, yep. I don't know why it's not maximizing. I don't know why. I don't know why it's not. Okay, normally.
You can maximize with shift and doing a scroll.
What?
But you can maximize with shift and doing a scroll with the wheel.
Okay, nice. As you can see, this fantastic guy named José Luis Vilas is one of the developers of XMake. Okay, and now it is possible to call from here. You can call the image.j, but I would like to open with image.j. I don't know, maybe I have a different version of it. For this, and you can trace one profile such like this, and you can image profile. I was somewhere there. I don't know where it is right now, but you plot profile here, and you can get the profile of this. This is just to show. Let me go back to the figure to show that the values we were using have been correctly represented. As you observe, we used the thickness of the outer and inner surroundings, which will be the same, is about of the size of the biggest ribosome we can find, and divided by the sampling rate, it would be around 24. So more or less, as you can see, it's maybe better here. You have the membrane, inner surroundings, outer surroundings, and about 50, considering this between 4 and 5 pixel thickness of the area of the membrane. Sizes seem to be correct. The profile, I'm not, okay, I'm going to tell it again, but just it is just explicative. It's a little bit out of the scope of this course, and maybe most of you, the ones familiar with Scipion, will know about it. Once you have this slice, which is obtained from the list, double click on it, you can go to you can go in the viewer to File somewhere here and open with ImageJ, which will display this toolbar. Then you can select this line, click and drag to draw it, and finally analyze plot profile, which will generate automatically this figure. Okay, now you get, since you have got it. Nice, Dimitri. Thanks for the question. So now we are sure, and this is to provide a clear visualization and conceptual understanding of how it works. Now we are ready to move to the graphs protocol. Okay. So the first input of this protocol, thanks to you, Dimitri, is just the segmented membranes we have pre-processed before. So the result of the Pyseg protocol. This second parameter is used to more or less determine the density, how dense the graphs net is going to be. So a very dense net of graphs will take a lot of time, calculation time, and it's more it should be used when you are trying to locate very small membrane particles. In this case, we are looking for ribosomes, which is a very big particle, which we are looking for the ones which are bonded to the membrane, and we are going to use a sigma of 2. You can these values depends for sure on the data set, and regarding with respecting to the default one, it is just the reference which has to be considered to decrease or increase or let it be as default, depending on your data set and on your problem. Here, we with this other parameter, we are going to specify how far can we go from the membrane to the outside. The final edge is the thickness of the outer or inner surroundings areas that we have determined before. You can, but not always the distance is in a straight line. It can be also due to flexibility, for example, a curved line. So you can determine a value which ends considering this curved line length, which is smaller, for example, than how far is the edge of the other and inner surrounding areas. This wizard will automatically bring you the value that you have used before here when you were determining the thickness of those areas. So by default, we expect this value to be the same, but you can play with it and read the explanation. And also in the documentation, I have added some notes in case you have to tune it. So let's execute this, and this protocol, it's the one with the highest elapsed time for execution. In my machine, it was about 20 minutes. I expect in these machines to be a little bit smaller than that. So I think there is a good moment to take a short break of about 10 minutes. During this break, I'll be here to solve any questions or talk about life, whatever you want. And so we'll continue. Hope it has finished. If not, it will be close to it at a quarter, more or less a quarter to 5 or 10 to 5. Philosophy session. This philosophy session will be. I hope next year it is all in person and we can have it and in a post course session.
Also, like on the evenings.
Yeah.
With a wine or a beer.
Yeah, you know what I mean.
Yeah.
Yeah, it would be a pleasure.
We cannot do it in Barcelona or Ibiza, no? Can we?
Barcelona.
Yeah.
You can come to Madrid, Dimitri. You can stay at my place. Okay. Luca, okay, I'm going to, yeah, I can show again how it works. Let's go back to the Pyseg membrane. ImageJ is a very powerful tool which is also integrated in the XMIP viewer. It can do a lot of things that I don't know how to do, but a lot of people here, the processing, the image processing team works a lot from it and know a lot how to use it. I only know such a few of the basic usage, like this one from the profile, because I think it's very, very, very useful for when you are analyzing the, to think a little bit about the sizes and so on. So once you are here in the segmentations panel, you once you want. And this one, it's a spherical. It's the one that's most is easier. It and to be perfect for a profile. Double click on it. If the maximization button doesn't work, I don't know why it isn't working for me in this machine. You can click. You can use the mouse wheel while pressing the Alt, not the Alt, the Shift key on your keyboard, and that way, yeah, it behaves better. Not as better as expected, but okay, well enough. You can see, I haven't mentioned before, you can dynamically you are monitoring the values from the position of the cursor. At this point, you can open the ImageJ. I don't know why it is complaining now. Oh, I don't know what happened. Oh, okay, let's go back. Let me go back to the previous, because maybe I was messing something up before. Okay, this is because I'm talking and talking, and sometimes I make mistakes instead of do things correctly. Okay. Image J. Okay, image J is open this, which is trying to open the full volume. I can forget about this because I want to work with this slice. And then you can click on this line icon and trace the line that will be used to trace the profile. Example, this. And with this, you go back to the image J. I don't know where is. Didn't render. Oh, someone from XMIP here. I don't know where it didn't render correctly. Oh yeah, now it is here. I don't know. Maybe there is some rendering problems because the graphs calculation is spends a lot of calculation resources from the machine, and maybe it's being a little bit difficult for a machine to work with all of it. Okay, I clicked here. I think it's maybe due to the graphs. I've clicked here in the blank space, and after that action, it was able to render. But do not worry about this. All this stuff is due to the graphs because at the first point, at the first stages of the calculations, it's calling a very powerful program called Disperse, which use all the resources present in your machine for calculations. And sometimes at the beginning of the calculations, it can be a little bit difficult to carry any other graphical operation. So, did you be able to render it, Luca? Oh yeah, cool. So finally, let's click on Analyze and Histogram. No, sorry, Analyze and Profile. There, plot profile. Yeah, this is it. And this way you get the CAD representation, the profile representation of this, and it is, you can directly more or less measure the thicknesses here by using the monitoring functionality of the viewer, but I think, at least for this tutorial, and I usually prefer that view because it is more precise when I'm trying to determine some sizes of the data and so on. I think it's quite useful functionality of the XMIP viewer. Before continue planning the evenings of the tomorrow of the next year's course. Oh. Any other question or anything I can help you with? I think it won't take so long this to finish. This is the longest execution we have for today, and I think we're going to be a little bit delayed in our time. Those who has to leave at 5, it's feel free to do that. Those ones who want to continue, I expect that between being optimistic, 5:15, between 5:15 and 5:30. No longer than 5:30, everything in the tutorial should have been finished. Evening this year. Next year we'll see, Dimitri. Cool. Okay, so while it's finishing, let's, those who has to leave, don't worry, because everything is explained in the documentation until the last step. So while it's finishing, let me comment a little bit what we are going to find in the results of the graphs. This representation, which is again with the fancy viewer, which includes some modes. It has been internally developed, and maybe this plugin has to be renamed. Maybe we have to rename it to Scipion and Fancy. Would be nice. Okay. As you can see, these are the membranes labeled. These labels doesn't have to be the material index used before. It's just used during the tutorial to be referred to the target membranes we are working with. So as you can see, this represents, for example, let's focus on this one, the membrane, and the graphs, the density connected vertices, the different minima which has been connected in terms of density from the membrane to the inside, to the inner surroundings and to the outer surroundings, considering the segmentation masks used obtained before in the Pyseg, and considering the density, which has been the value of the sigma, more or less, which can be interpreted as the density of the graph, and the distance, which can be the graphs can extend from the membrane to the outside and to the inside. The filaments will be a refinement of this result, just with any other parameters and filters to have, instead of different connected local different connected nodes, will have only the initial and the final node, the connection of only two nodes, which will be the beginning and the end of the filament, which will be used finally for the picking. So let's check. Oh, it's taking longer than in my machine. Unexpected, considering this machine is. I'm afraid, as we've said before, that these machines. Oh, is everything all right there? It's okay. Maybe she. Oh, she left. Okay, I was going to mute his or her. So I'm afraid that this hard disks, as said before, aren't SSD. So it seems that the writing time is taking so long. I expect it not to be not so long than from this moment, because it shouldn't be close to the end, I hope. Meanwhile, we can discuss the results we are going to obtain later, so we can parallelize, we can go through these tasks in parallel. So what are we going to do with the other? Why I shouldn't think about this before. Let me open the protocol in my local machine so we can have both things together, the tutorial and the parameter. Okay, more or less. Oh. Cool. So when the graphs are finished, we are going to refine them to get the filaments. Let's discuss about the parameters we are going to introduce once it's finished. And as we can observe, we have 4 tabs here. The input is very easy to do because it is only the result of the graphs. Let's set the pointer here. And then we have these twin tabs. One which is they present the same parameters, and they can be used to define the geometrical parameters that will be considered to generate the graphs, the filaments from the graphs, considering different areas from the initial segmentation. So in this case, for example, I'm going to forget about the sources. I'm going to specify it is the membrane. I'm going to pick, I want the filaments to be from the membrane to the outer surroundings. And Dimitri, no, the filament are...
Sorry.
Oh, no, it's okay. The filaments are there's like a refinement of the graphs. The graphs are a mathematical object which is used to connect nodes that may represent any different entity in a phase space. Let me try to explain it. So, for example, in this case, we are looking for the lines which follow a determined, for example, density, and we are connecting minima, which are representing some values of the density, which seems to be or to follow a continuous trend. These are the graph lines we have been painting before. The filament is the name that has been given to the to the representation of the graph objects, but considering only the initial node and the final node within a set of conditions or constraints, which are the ones that we are going to determine using these tabs. Let me go back. Ooh, so long. My calculations, considering this. Oh, it is saving. Hope it won't take so long. It is like a deja vu. Okay, so in this case, we are not. It depends on the data set or the problem you're trying to solve. But in this case, we have these ribosomes which are located the outer surroundings of the membrane, and they are bonded to it. So apart from that, the outer surroundings area is much more thicker than the membrane one. So the metrics within the membrane doesn't matter quite a lot in this case, because all the important stuff, all the region of interest here is the outer surroundings. But it is essential, critical to determine which is the source area and which is the target area. But the constraints, the geometrical constraints, are not quite important here. For example, if you were trying to pick something which is from the outside to the inside across the membrane, it would be very, very critical to determine correctly that. But here we have three concepts. Let's explain these ones just to maybe clarify why I'm saying this of the sources in this case. Maybe it's not mathematically rigorous or correct to use these three words I've used here when designing this form, but the idea is to transmit, to make the user understand, at least conceptually, more or less, what does these parameters represent to use them properly. I'll update this to Armstrong to be all coherent in terms of units in the next code review. But for now, let me allow me to consider them in nanometers. So we are working with two metrics of length and one metrics which could be considered as a measurement of the flexibility. So when I say the Euclidean distance or length to the membrane is the straight line which goes from the membrane to the outer surround, from the edge of the outer edge, in this case, of the membrane to the edge of the outer surrounding area. With the profile, it is very, very easy to understand. But I think we have all this image in our head. So I don't want filaments. My filaments, I'm going to pick them from my graphs, the one which, if I measured them from 0 to 30, which is the maximum size I expect for my particles, I picked these intermediate values. I could, but I won't, for example, because it is not necessary, as long as if the ribosome size is between 25 and 30 or between 20 and 30, I'm not interested in the lower values, so I can use, for example, 20 here. We'll fix the parameters. I have the correct ones in the doc. I think more or less these are the same, but it is a pure coincidence. The other length constraint is regarding the geodesic length. Geodesic length, as Antonio explained before, is measured like in a curved line. For example, this Antonio usually uses an example which I think is very clarifying, which is, imagine Google Maps. You want to go from one point to another point, from a source point to a target point. The Euclidean distance is the straight line which goes from the source point to the target point, while the geodesic length will be the distance across the streets, which won't be, unless a few cases, a few range of cases, won't be a straight line, would be something like this across the streets, which is what we call curved. So if we consider some kind of flexibility in our particles, we should have to consider different, something like this, I don't know. We can think that at least this distance, it is not very scandalous to think that can be the double, for example. So I can, maybe I'm going to say from a very rigid conformation, 30 to 60. And the flexibility is a range, which is more or less, to have a reference value, the ratio between the geodesic and the Euclidean length as max value. So in this case, could be 2, but you can pick a range between 1 and 2 or 1 and 1.5. And these 3 constraints together are applied in this area. This is why they have no effect here, considering we are only picking out in the other surroundings, and the membrane is so slim with respect to the thickness of the other surrounding area that it doesn't have so much effect. And finally, we have a refinement. Once we have our filaments, we can specify, for example, it can be more critical. Okay, see you tomorrow, Pablo. Thank you. We have a final range. For example, imagine that you have particles that are going from the outside to the inside of the membrane, across the membrane. You can refine these filaments, the ones you have obtained after combining the constraints in the source area, the constraints on the target area, and with those resulting filaments, you can again apply a final filter, which is from all of them, considering it traced in the correct areas, and after the constraints fixed before, apply this other among the whole distance, which among not considering the areas anymore and so on, just the final over the final product. And again, we can fix this straight length, curved length, and this flexibility more or less indicator. It's a little bit complex. I think it's the last complex part of the tutorial, but I think I hope it to be more or less clear. Let's hope it has finished and we can just set them up and execute. If you have any doubt until this point, just let me know. Whoa, that doesn't look so good. I don't know why. It's taking much more longer than expected in my machine, but I wasn't expecting the one with the disk. We need 2 things, which is high velocity for writing and reading from disk, and a good high memory source, which is and as many CPUs as possible. And second and third aspect are fully covered by these machines, but I wasn't expecting the disks to be so slow. Okay. So I think if conceptually everything is clear until this point, Dimitri. I don't think it would it won't take any much more time. By the time it's finished, it can be some means to cover the rest of the core flow. What I propose is to continue a little bit until no much longer than half past 5, as said before, and continue explaining the critical aspects of the parameters while it's finished. Protocol provides performance. Yeah, Bram. Indeed, Pablo is working on Junior in terms of performance, and there's a lot of stuff that will be making everything even better. But in this case, the graphs calculations are being carried out via third-party software called Disperse, which I don't know if it's possible. Maybe Antonio can clarify this. It's taking.
Yeah. I don't know. Did you do the smoothing exactly as before?
Yes. Let me. This is the parameters I've shown. Let me. Someone is ringing the bell. Sorry, I'll be back in a minute. Sorry again for inconvenience. Murphy's law is very, very powerful today.
I think you are saying that this is going slower than you expected.
I don't know, because I was, but yesterday I have the same impression that even though these machines are powerful, more powerful than ours, things were going a little bit slower compared with us. I don't know specific details about this. I know the RAM and this number of CPUs, but I don't know anything about the disk. Maybe there's the problem.
Yeah, the parameter are the same as you remember is 2.
Yeah,
okay.
I have them. I have the project here in my local machine.
And the maximum distance. Okay.
Yeah, it's the same, and it took me 23 means, and here it's 37 something. It's this is why I got completely surprised. I don't know why it's taking so long.
I don't know, probably is this the frequency of this computer slower?
I don't know, but it is going.
Well, perhaps we can continue with the Solvit project because we have the output and we can.
Yeah, I was expecting it to be okay. Good idea. Tamara always. yeah. Murphy is always there. Okay, so to finish it and continue the description of the parameters, just I suggest you, as José Luis Vilas has said, that we can open this project from the project list, the ones yours is done. Have you hacked my machine, Dimitri?
No, I'm serious. I did it. I clicked it just before. I refreshed it and it's done. So I guess you're also close to the end. When is which is the latest number you have in the run a standard output?
Let me have a look.
My number is 232. So you can see how far you're there. Yeah, quite far. Maybe I clicked before while you were explaining. I started it.
Maybe. Okay, but for sure, as you can see, in my machine, it was quite fast. I don't know what's the problem in these ones. Okay, so let's move to sum up in a better way and not be stopped by this. For the ones which are currently working here, please remain here. And for the others, please look for this project on the project list. It should be somewhere here, and open day 2 picking memseg and Pyseg. So the graphs just the same as observed. Okay. Yeah, always. We'll discuss about Murphy next year, maybe. We can use the fancy 3D viewer again by clicking on Analyze when selecting the graphs protocol, and by double-clicking on one of each elements. Each of this one represents a vesicle. The 3D viewer should be displayed with the but maybe okay. Here's done too. Maybe okay. I maybe do I have the slowest machine ever? Would be very funny. Ooh, okay. Maybe. Welcome to the club. Yeah. I'll be. I'm not in that club. I'm not. Okay. So I'll continue. This is nothing bad. So as you can.
Sorry.
Yeah.
How did you open this vesicle visualization object manager?
Yeah, I just select the graphs protocol once it's finished, and click on Analyze Results. That would display this window. And by double-clicking on one of these elements, we could have this window displayed. Mine can be a little bit slow due to the fact that the graphs is still running. So as you can see, just very, very fast. You can use the slicing, you can check the orientation of the slices and do whatever you want with it, just to play different representations, the slicing. With the filaments, you can have the cutting point, and you can paint the using different criteria. For example, the membrane Euclidean distance or the geodesic one, and so on. You can explore and play with it, but just for visualization. And again, it is completely and fully detailed explained here in the documentation. Regarding the graphs, everything explained before is again here in the documentation, and the result should look like this. As you can see, it's a very refined version of the parameters. Let's have a look. Dimitri, I'm going to change your machine by mine. Okay, let's go back here. Okay, just to have a quick overview. No, the world is laughing at me now. Murphy is laughing at me now. Okay, meanwhile, let's check what parameters were used here. As you can observe, indeed, I don't know if this has the parameters. Yeah, Okay, you can filter them much more using higher values. Maybe I wasn't thinking of explaining it so in detail, but regarding the graphs issue, I've done it. So I think it can be faster, quite faster, if we, for example, use from 20 to 30 or from 30 to 60, because we're considering here that I only want the range of values in considering the straight length, which suits to the expected values, the mean and the max values of the ribosome, and considering just some orientation that can make the distance to be cured. I can go from the highest, for example, straight to the highest considering cured, and I can use the. You have a gray image. Yeah, you have to click on the boxes which are down. Click, for example, in the first one. Try to click the graphs one, which is the third, beginning from the top, from the bottom left corner. Maybe it takes a little bit long to if the graphs. Yeah, cool.
Because I don't have these boxes at the end, at the bottom.
Oh, okay. Yeah, maybe it has, if the graphs is still running, maybe it can take a little bit longer than usual to render the images. Okay, so with these values, we can refine it to make it be faster, but you have from 0 the canonical ones here in the tutorial. And okay, I was my my past myself was better than me, and for the tutorial it was using no filter here from 0 to the value, and using in the final filter the considerations I've considered before here, just during the explanation. But everything is completely well explained in the tutorial. So if we execute this in my machine, I think it was about 5 means, 7 means, something like this. The result would be as expected. Again, we can generate this with the analyzed results. Again, all the intermediate visualizations, as Antonio mentioned before, can be observed, can be displayed out of Scipion with PowerView, and inside Scipion we have the Tomo 3D internally, which was internally developed, the fancy viewer for all of us. Let me double click on one of these. This delay seems that my graphs hasn't finished yet. Sure. Oh yeah. Oh yeah. I'm in your club now, Dimitri. I'm in your club, man. Look at this. Okay. It was much more longer than expected. Yeah, as you can see, it seems to be slow and slow. From the viewer, it's more or less the same than before, that the representations varies a little bit. You have the net, which is the filtered net of graphs. Now there are the filaments. The representations are the same as before. And you can play with the slices just to get faster than expected, just to get the sorry, I have a little delay. To check, for example, if you click on net slice, it is very useful because net slice representation represents the cutting point of the filaments with the current slice. You can move the current slice and check the cutting points. Some of them will correspond with a ribosome, some of them not, and we'll determine them after picking with the 2D classification. We are close to the end. There are some executions to done, but the hard thing to explain, it's completely done. Any doubts until here? No? Okay. Okay. This is what I wanted to read. Okay, so finally we can move to the picking protocol. The picking protocol is simpler than the in terms of form than the one used for the filament calculations. You only have to indicate the protocol, the fields protocol, the pointer to that, and the tomograms in which you want to pick the particles, which can be the same used or different. It depends on you. For example, you can have different reconstructions of your tomogram, one with Nova, one with JGSoft, one with iMod, and maybe you try to reconstruct or perform the subtomoral averaging using one or the other to get one different kinds of information or comparing which one suits better to your data set and so on. So you can specify it. For us, it will be the same, the importing ones. And yeah, Dimitri, it is the as you can see here, the import, the ones used, the original data. The less mathematically adulterated product, the better. And finally, we can refine all the. Okay, this is okay. 1 second. You have to select the area in which you want to pick. In our case, it's the outer surroundings, and this is the critical option that was detailedly explained by Antonio before, which was, if you remember, the one from the cutting point of the filament with the membrane, or the projected local minima, which was those little projections. To this second option will takes us to a scenario of overpicking, but it's better than miss or low picking because we are not leaving back any non-picked particles, and we can filter and refine everything later. So better more than less in this case. And finally, you can apply a small filter that won't. It is not edited here because we are going to use another protocol which filter by distance and by another by normal very, very fast, just not to keep you here until very late. Was trying to be a lower, faster than finishing at 5:30, but it won't happen today. Okay, so again, we have another very, very, very. I know you'll be here until the end here with me, Dimitri. Again, we can have a fancy representation with our fancy 3D viewer of the picking, taking long to render, which is this. It's quite close, quite similar to the one shown by Antonio. Indeed, he showed both representations, the ParaView one and this one. As you can see, you can represent the peaks, which are the picked particles, the coordinates of the picked particles, represented with an orange small sphere, the directions with which are the normals, and the surface, which is the representation of the membrane. Why it is not rendering it? I don't know. Machine is not going good. Okay, so meanwhile, I'll continue. So at this point, I don't know, it's not. No? Okay. At this point, we are going to carry out two filtering operations, which will be performed before the 2D classification, which is the final step of today. So we're going to filter by normal. What does... Oh. Indeed, it was loading, but the machine is going slow, very, very slow. This is a representation. Oh, shit. You can paint the boxes. I shouldn't click there because it's not used for this kind of problem. And this is a different color tab with respecting the... its memory is full with all of this information. Okay, so here with these colors, you can represent, again, the same as shown in the documentation. Here you can represent the directions. And I was expecting to have the vesicles, but I don't get them. Maybe it's another version of the software, the one I have. But it's wide enough to get it. Okay, so we're going to carry out some other operations, which are removing duplicates. What does it mean? It means that maybe due to the fact that we have used options that can carry out, that can take us to an scenario of overpicking, we're going to use a criteria, which is the particles which have been picked closer than a distance will be considered as the same particle. And I think it takes the mean position and orientation of each set of particles considered to be the same under this criteria. So for this, we have this remove duplicates protocol, which is a part of Tomo 3D plugin, which has more things apart from the fancy viewer. And it is very, very easy to fill and run. So we only have to select the coordinates that we have obtained here in the picking protocol. And we have considered here a radius of 10. In this case, they are in pixels. So considering the pixels, I think it is the discussion was made here. Yeah. So we have if we consider the middle of the ribosome, and we consider the biggest size, which is 300 Armstrong, and we divide it by, this should be an 8, by the voxel size, it is more or less 11 voxel. I use 10 voxel up, voxel down, it's okay, but more or less to have reference distance to apply it. After that, this is a very, very fast. All these executions take just a few seconds. We have gone through from more than 2,000 particles picked to 641 particles. Which means that there was a lot of overpicking. The next filtering operation, again, I don't forget, you can also again use this to represent the new the new position. I think maybe it was this what I was representing before. You can observe after the filter by distance operation that the particles, the number of particles has critically decreased, and you can also paint its normals and so on, and you can play with all of this stuff. Finally, we're going to filter by normal. What does it means? It means that you can have different orientations of your particles with respect to the normal. You can have, for example, some which should be there. You can have these ones. I don't know. So imagine you could determine a range of values of how can a particle to be correctly oriented, how different can be from the normal normal direction. This is what this protocol does. Where let me explain it before. We can filter. We can also filter by tilt angle, which is not carried out during this tutorial. But we are being quite generous with the orientation. So we are telling it that it can be a 30-degree different from the normal direction. All of this, all the particles within that which are contained in that range will be considered as good ones, and the rest will be considered as bad ones, and as a consequence they will be removed from the set. Here we found a problem that this protocol requires an object that we don't have, which is the so-called output meshes, an object which is the set of meshes. To generate it is very, very easy. It's the protocol explained this morning, so long ago, this morning, by David, which generates the surface, polygonal surface, which contains all these coordinates just to be able to determine the different orientations and operate with them, just to apply this filter. So this is summarizing. This is a representation which is required to apply of the data, which is required to apply the filter by normal protocol. So we just generate it, and that's it. After using it, we have, so as you can see here, fit vesicles, and we move from 641 particles to 285 particles. So at this point, we are more or less happy with the particles we have. They are good candidates to represent a physical entity of type ribosome bound to the membrane. This next protocol is one which is very, very used. It's just to extract the particles, the subvolumes, subtomograms from the tomogram, which is just cropping on each of those coordinates with a box size of an specified size. So again, just the same as it was made in when picking the particles, you can specify the tomogram source if you want to do it with in the same tomograms as the ones used for the picking or other, just to check that this option works correctly, even though you are using the same. I try just to use it as a reminder for me, just to explain this and puntualize and remark this you can use the other. In this case, I'm using the same, the import. But for example, you can have another kind of reconstruction you want to use for the begin. We're not going to downsample it. The box size is again determined thing a little bit, which is quite critical here. So we are going to ignore the wizard. This is because we are working with Pyseg, and how the origin of the coordinates system is referred. It means that the center of the coordinates, the center of the box we are going to define, is on the membrane itself. So if we want to have in our box a particle of 300 angstrom, and considering that the center of the box is on the membrane, we have to consider the double for the box size. Why is that? Because you will have 300 from the membrane to the outer surroundings and 300 to the inner surroundings. And with the sampling rate, we can estimate the size, which will be, in this case, 44 voxels. See you tomorrow, Sarah. Thank you for coming. And once we have extracted the particles, bye, Luca. Or, oh no, maybe you are here and you're saying bye too. So, okay. With here, we only have, which is very, very, we have the same number of items as the coordinates, but with a box size. We have been cropped from the volume. We can observe it's not quite illustrative, but as you can see, we have some small area or some small volume from which has been cropped from our tomogram. For example, you can see here. It is not quite to see here, but maybe you can imagine with a very high degree. Oof, this is like a membrane. This is like a round ball. Let's see if it is a ribosome or not. That seems to be a good particle. Finally, it's been quite hard to reach this point, but we have survived. So, Pyseg classification. It is, as explained before by Antonio, it offers different options, which will be briefly discussed here. It offers different clustering algorithms, which are the two classical ones, agglomerative clustering and k-means, but those ones need, as you can see, all the parameters change, to specify the number of classes. Maybe normally you don't know if you're working with experimental data, as Antonio said before. So we suggest affinity propagation because it works well and it determines more or less the number of classes you have. Here we have to set the pointer to the extracted subtomograms. And again, we have a problem here. We need a mask just to use it to indicate a region of interest in which the rotational average will be carried out. Oh, we are close to the end. Yeah, it is 2D classification because you are around an axis. You are making a rotational average, which is the result of that operation is an image. It's a 2D. It's a 2D image, sure, by definition. Let me.
So Yeah, I mean, sorry for interrupt you.
Oh, Antonio, you're more than welcome.
Sorry for interrupt you, Jorge. Maybe I'm more fresh than you because
For
I
sure.
recently joined. Okay, so why the rotational average? Because at this point, we don't know the rotation of these particles around this axis. And then we do this rotational average in order to flatten the particle into 2D with this purpose, not to consider the orientation with respect the in-play angle, because we don't know still what this angle is, the good one. In addition, when we do this radial average, we also increase the signal to noise, the contrast, for every particle. So this is another reason why we do this.
Okay, thank you, Antonio. Yeah, and regarding the question of the imagery, yeah, if you pick each plane around an axis and rotate everything and make the mean of all of this, in the end you have a plane. So in the end, the representative of each class will be a 2D image. That's why it's a 2D classification. And again, correct me, Antonio, if I maybe if you think I'm wrong, because yeah, as you have said before, you're fresher than me. Thanks to you, Dimitri. So just very fast before all the people leave. At this point, we need a mask to determine the region of interest. It can be very easily created with XMIP3. It is quite well explained again in the documentation. This is a very critical point because we have to be sure that we are taking a region which is small enough to contain the whole particle, a part of the membrane, a little bit of the inner surroundings, and more or less be as close to the size of the particle as possible. That way to provide a highest signal when you are performing the rotational average and having better results. So this is very critical. Everything is very well explained here. You can create from a geometry a cylinder, which is what we have said, and the sampling rate, considering it, the critical parameters are the radius and the shift. In this case, to consider the radius, we have again the same reasoning as before. We have the mid thickness from the geometrical center is around 150 Armstrong, and considering the sampling rate, it is more or less 11 voxels, and we're going to add 1 to leave some margin. Then the other critical parameter is the shift. The shift, it is necessary because we are going to move it a little bit down, so some of the membrane is contained on the cylinder because the origin is the center of the box. So we have to shift it a little bit to the bottom, so to ensure that the membrane and a small portion of the inner surroundings is contained. And to determine this shifting, we are again, all the reasoning is here. It is 6 pixels because 6 multiplied by the sampling rate is about 82 Armstrong, which is approximately the 60 Armstrong considered for the membrane thickness and 20 Armstrong considered for the inner surroundings. So at the beginning, with a shift of 6 to the bottom, we should be able to cover the region of interest. And finally, the same with the height of the cylinder. We are going to make it as high as the maximum shape expected from our particle. And considering the particle, the membrane, the inner surroundings, so more or less 28. And we're leaving a couple of pixels of margin. We rounded it to 30. So with these parameters, which is this mask is quite critical, we obtained this representation, as you can see, with the slices, with the data viewer from XMIP, the different slices of the cylinder. We have also used, I forgot it, this option to smooth, apply a Gaussian sigma, a Gaussian filter to smooth the borders. And which is interesting for the subtomolar averaging, which is not being covered in this tutorial, but will be tomorrow. With this mask, we are able finally to fill these parameters, and with our particles, our mask, I've used an intermediate filter of 2 voxels to provide a proper representation of the results. You can play with this just to get to increase or to get a better visualization of your results. Leave all the parameters by default, and if you click on execute, we obtain 2 classes and a set of subtomograms which can be classified. They contain the information about which class they belong to. Normally, there are more classes than 2. For example, if we didn't perform the filter by normal, probably there would be 4 or 5. For example, in my different executions of this workflow when we were preparing the tutorials, I was with some combinations of this proceeding. I was able to find even 5 classes, 6 classes. But at this time, after having applied all these filters, the number of classes get reduced. In this case, we only observe 2 different classes, which correspond to the membrane without anything, or a membrane with a density, which is like a Christmas tree, quite appropriate for this time. And these particles are quite good potential particles for reconstructing our ribosome. So using this viewer, we can select one or the other class and generate a subset which only contains the elements which belong to that class, which is this result. I name it class 1. And at that point is where the tutorial finishes. So as you can see, how to interpret the result is just like rotating 90 degrees, because the XMIP viewer with this geometry is rotating 90 degrees the image to represent more in the squared representation you can see here. So the correct interpretation would be something like this. This is the rotation axis, and this is half of the particle whose plane has been rotated and averaged. So this is the result of the classes. And if you, with all the knowledge you are going to acquire tomorrow in the whole day dedicated for tomography averaging, you can continue processing it. This is not such a very good result, and we have some doubts about the handiness, but just to show you something, this is something like this. Often with that data, it is there's missing wedge effect, and it is not quite a good resolution, but indeed, just for a beginner like me, it is more or less a ribosome.
Yeah, I think that the most important thing is that this is just a single tomogram, bin 4.
Sure.
I think that picking this average is made with a pixel size, I don't know, 2.20 angstrom or 30 angstrom or something like that.
Yeah.
So it's not possible to go so much. Yeah. Usually in subtomolan average, you cannot go longer than 3 times your pixel size. It's very hard to reach that resolution. So in this case, is unless you go to more tomogram and more higher resolution data, so it's hard to go farther than this.
Yeah, I think it was about 50 or 54. I think it was the resolution of this. So it's the limit 3 times 40, it's about 14, it's about 40.
Yeah, unless you are able to process more particles, you cannot start to think about it.
Sure. I'm quite impressed about the result obtained. This result I was able to obtain it helped by Antonio and also by our Anna and Patricia from our processing team. Because I'm a software developer, I work with all of this stuff, and I try to learn because it's a very transversal work, and we collaborate every day with the structural biologists to develop our solutions. So it is. I was very impressive to obtain this with, as Antonio said before, just one tomogram. With no purification, with such a small size, and which means that high sampling rate, and I think it's quite good. But it is just to illustrate that indeed, what seems to be something in the end, at the real finishing point of this tutorial, which is the 2D classification, for real is something which is big, which seems to be a ribosome, and it's bounded to the membrane. So it's the power of all these tools and the interoperability between one and the other offered by Scipion. Everything, the details, the missing wedge effect, everything related to the obtention of this will be explained, as Jose Luis Vilas is saying in the chat, tomorrow in the tomorrow session, which will be the full day dedicated to it. So sorry for taking so long. Thank you for being here until the end, and for your patience. And for me, it was a really nice day, and it was even fun for me. And we have been some trouble with annotation too, but it was quite good. So thanks to all for coming. Antonio, thank you very much for your presentation, for coming and joining this workshop.
Okay.
And see you all tomorrow.
See you.
See you all tomorrow. Now lab is waiting for me.